Welcome back, everybody. This is again Professor Queen, and I will be lecturing on the third and the final part of chapter 19, which is on the cardiovascular system and blood vessels. And we are going to move on and continue on with the control of blood flow. Let's take a look at the words tissue and perfusion. Tissue perfusion. This is blood flow through body tissues, and they're involved in the delivery of oxygen and nutrients and the removal of waste from the tissue cells. And then you have also part of it gas exchange, which is happening in the lungs, and absorption of nutrients, and this is actually right along the digestive tract, and the formation of urine. Of course, this is part of excretion in the kidneys. The rate of flow should be precisely right amount in order to provide proper function to that tissue or organ. If it gets too fast or if it gets too slow, then the proper function to that organ may not be achieved. So the rate of flow is controlled by two factors, and these are your extrinsic and as well as intrinsic factors. The extrinsic factors involve sympathetic nervous system and hormone control, and these factors control blood flow through the whole body. They act on the smooth muscles of the arteries to reduce flow to regions that would need it the least. And then the intrinsic control is actually the auto regulatory or the local control of blood flow. This is where blood flow is adjusted locally to meet the specific needs of different types of tissues. Now, local arteries that feed the capillaries can undergo either vasoconstriction or vasodilation. They modify the size of their diameters in order to provide more blood, or vasoconstriction if in order to limit the flow of blood in a particular tissue. Organs regulate their own blood flow by varying resistance of their own arterioles. So here, this is a good diagram that you can use to review the differences. You could compare and contrast the extrinsic and intrinsic control. Okay, and here it's showing that the intrinsic control is entirely from coming from within the tissue or the organ. These would use like local hormones, paracrines, or properties of the muscle tissues. And this is also known as the self-regulatory mechanism of the tissue, or the auto-regulation regulatory mechanism of the tissues. The extrinsic control, on the other hand, is from outside the tissue or the organ, and this makes use of nerves and hormones. Now, I'd like you to know that there are examples that is in your textbook. You find them, for instance, in varying parts of some of them. We already took them, like in the stroke volume, the heart. Look at page 697. You revisit them in 698, and then you take a look at figure 19.16 regarding arteriolar diameter. And then in chapter 25, although we have not really visited chapter 25, take a look and try to understand the glomerular filtration in the kidneys, so you will understand these controls. So let's take a look at the last of the control of blood flow. For instance, when you are redistributing blood during an exercise, and you know that exercise really moves blood really very fast. It involves the movement of many organs and many parts of the body, most especially the skeletal muscle. You know, at rest, skeletal muscles receive about only 20% of the total blood in the body. But during exercise, the skeletal muscle can receive over 70% of the blood. Now that's really a good amount of blood getting into the muscles. Of course, they deserve it. You know, the muscles are moving actively. They need energy. Therefore, the body really is just infusing more blood into the muscles. The in the intrinsic control, uh, the skeletal muscles um, have arteries around them, and these arteries dilate, increasing blood flow into the muscles. And then extrinsically, okay, there's going to be decreased blood flow to other organs such as kidneys and digestive organs. So uh, the decreased blood flow from another organ is a chance for some volume of blood to be directed into the skeletal muscles, and that's the reason why from 20% it went up to 70%. The mean arterial pressure is maintained despite the dilation of skeletal muscle arterioles. Most especially, you need to maintain the mean arterial pressure in vital organs that you cannot really reduce blood flow. And here is actually the distribution of blood flow, okay, at rest and during an exercise. Okay, this particular, let me take a look at whether I can use this laser pointer. Okay, at at rest, take a look at the skeletal muscles receiving only 1,200 ml per minute. Okay, 1,200 ml per minute. Out of 5,800 ml of blood. Imagine how much blood we have, right? And that's about 20% of the total blood only. And then it rises into 12,500, which is pretty much out of the 17,500 ml that that's actually flowing now whenever we're exercising. You could just imagine the total blood flow increases from 5,800 to 7,500. Now, where did all the blood come from? Well, we have reservoir of blood. Our veins are reservoir of blood, and when we are not moving, those reservoir just get the blood in there. But when we move, they empty those reservoir and they pull it to different places. And right here, the skeletal muscle receives about 70% of the total blood flow during a strenuous exercise, and you could see it. But the only thing that is not changing, though, is actually the brain. One of the things that does not change is the brain. All others would either diminish, like for instance, in the abdominal region, you have 1,400 at rest, but now it is only 600 during a strenuous exercise. Okay, the kidneys will have more when it is at rest, and during a strenuous exercise, it is diminished. Okay, the there are other there are other regions, other tissues where there's always a diminishing flow, but the heart and the brain will receive the same amount, 750 ml. It cannot change. And then the heart would receive more together with the skeletal muscle, because these are both the ones that are actively engaged when we are in strenuous exercise. So, uh, pretty much, let's take a look at what these autoregulatory mechanisms are. The intrinsic regulation of blood flow. Okay, autoregulation makes use of local conditions, intrinsic conditions that regulate blood flow to a specific area. Now, reactive hyperemia is an instance where increased blood flow to an area happens due to intrinsic factors. And there are two types of intrinsic mechanism. Both would determine the final autoregulatory response. One is by way of metabolic controls, and the other one is by way of myogenic controls. Well, just by these words, you know that The first one would probably be involving chemicals that are byproducts of metabolism. And then the myogenic control, I think, is actually like the muscles are involved here because myo stands for muscle. So we'll find out. Let's find out what they really are. So, in the metabolic control, increase in tissue metabolic activities would pretty much result in declining levels of oxygen. Okay. Once you have a declining level of oxygen, there's going to be increasing levels also of metabolic products such as hydrogen ion, potassium, adenosine, and prostaglandins. Now, the effects of the change in levels of local chemicals can actually have uh, direct relaxation, can cause actually direct relaxation of arterioles and relaxation of precapillary sphincters. Whenever you have the precapillary sphincters, and if you remember that these are actually smooth muscles that are in the precapillary region, and when they are relaxed, they definitely would open up, right? The sphincter will not close that area, it will open up. And that would increase blood flow into the tissue. And this what do you call this decline, this metabolic activity can also cause the release of nitric oxide. Nitric oxide is a powerful vasodilator by the endothelial cells. The endothelial cells are the ones that produce or release the nitric oxide, and it will cause vasodilation. So first you have the relaxation of your precapillary sphincter, which will pretty much like eventually allow more flow of blood right through the capillaries. And then your nitric oxide is a powerful vasodilator. So eventually you're going to have an increased flow in that particular region. So endothelins, substance also released from the endothelium, are actually potent vasoconstriction, which is pretty much like I think the reverse, or it has a reverse action from nitric oxide. Nitric oxide and nitric oxide and endothelins usually should have a balance unless the flow is inadequate. In which case, if there is inadequate flow, the nitric oxide must win control because nitric oxide is a vasodilator. Okay, so the body will be, or the endothelial cells will produce more of the nitric oxide, okay, and less of the endothelins. But in the event that it is not necessary to either dilate or constrict a blood vessel, they should be balanced because one is a vasoconstrictor, which is your endothelin, and the nitric oxide is a vasodilator. Now, take note that inflammatory chemicals can also cause vasodilation. Okay, now let's take a look at myogenic controls. Now, in myogenic responses, local vascular smooth muscles respond to changes in mean arterial pressure to keep the perfusion constant, or the perfusion of blood into the tissues constant, to avoid damage to the tissue in question. Now, passive stretch, okay, will eventually cause, or it's actually caused by increased mean arterial pressure. It is actually caused by an increase in mean arterial pressure as it stretches the vessel wall more than normal. Here, the smooth muscles would respond by constricting, causing decreased blood flow to the tissues. So it's going to be like a reverse. Okay. Now, reduced stretch. Okay, this is when your a decrease in mean arterial pressure causes less stretch than normal. The smooth muscle responds, okay, by dilating, causing the increased blood flow to the tissues. So again, it is actually to pretty much like reverse the situation. Now, after the short-term regulation, let's take a look at the long-term autoregulation. This occurs when short-term autoregulation cannot anymore meet the tissue nutrient requirements. The long-term autoregulation may take weeks, though, or months to increase blood supply, because here it involves the number of vesicles to increase in amount, meaning you are going to have angiogenesis, and the existing blood vessels also would enlarge. These uh, these angiogenesis is very common in heart, where the coronary blood vessels are occluded, or throughout the body, with among people living in high altitude areas. All right. So let's take a look at here. Again, you're going to be comparing and what you call is comparing and contrasting the metabolic, okay, and myogenic. The intrinsic, rather, this is actually the intrinsic control and autoregulation, the intrinsic control and the extrinsic control, and what they do to the blood vessels. Okay, and in the intrinsic control, in the metabolic aspect, if there's going to be a decrease in oxygen, an increase in carbon dioxide, or hydrogen ion, potassium ion, and prostaglandins, adenosine, and nitric oxide, that's going to, the effect of this will be to uh, dilate the blood vessel. Okay, that's going to cause the dilation of the blood vessel. In the extrinsic level, both neural and hormonal, okay, the neural will, with regard, uh, when the neural will actually have a decrease in sympathetic tone, okay, and the hormonal, the atrial natriuretic peptide will cause vasodilation and would decrease blood pressure, which is a matter of fact, which is pretty much um, uh, the one and only, um, the one and only uh, chemical that is produced by the body, okay, among the other hormones that are actually produced by the body that involves blood pressure. The AMP is the only one that reduces blood pressure. The others, well, for instance, in the extrinsic control, uh, well, one of the intrinsic control, for instance, in the neural aspect, increased sympathetic tone will vasoconstrict a blood vessel and therefore increase blood pressure. And the other hormones work contrary to what the ANP, the atrial natriuretic peptide, would do. Like angiotensin 2, antidiuretic hormone, your epinephrine and norepinephrine, they all increase uh, blood pressure because the effect of these hormones are is actually to vasoconstrict. All right. And then in the intrinsic control, pretty much both myogenic and metabolic um, control is also going to cause vasoconstriction. Now, let's take a look at blood flow in special areas. For instance, in the skeletal muscles, blood flow varies with fiber type and activity. At rest, the myogenic and neural mechanism will predominate and would maintain flow at 1 liter per minute. Um, During active um, body movements or during exercise, hyperemia, um, or an increase in muscle activity, blood flow increases in direct proportion to metabolic activity. Local controls override the sympathetic vasoconstriction, and flow can increase actually 10 times. So, active hyperemia, pretty much during exercising okay, we are actually looking at the case of active hyperemia, which is during exercising, the skeletal muscle would have a decrease in oxygen. All the oxygen will be consumed, an increase in carbon dioxide, increase in hydrogen ion, and other metabolic factors in the extracellular fluid. This would eventually result in vasodilation of the arteries. Okay, they override extrinsic sympathetic input, and pretty much the effect of this will be after vasodilation, increased blood flow. Okay, which is active hyperemia into the skeletal muscles. What about the brain? What about the brain? Well, the blood flow to the brain must be constant because our neurons are very intolerant to ischemia. Flow averages about 750 ml per minute, and even during exercise, where everything is almost shunted into the skeletal muscles and into the heart, there should be no, or there should not be a decrease in blood flow to the brain. So it remains at 750 ml per minute. Okay. There are some control mechanisms such as your metabolic control. Decreased pH or increased carbon dioxide can cause marked vasodilation, and very high carbon dioxide level would depress the autoregulatory mechanism. And of course, in the myogenic controls, the decreased mean arterial pressures can cause the cerebral vessels to dilate. Okay, thus causing the mean arterial pressure. Nothing will be diminished when it comes to the brain. All right. Matter of fact, the brain is very vulnerable under extreme systemic pressure changes. And anytime the mean arterial pressure goes below 60 millimeters of mercury, it can cause fainting. And a mean arterial pressure above 160 millimeters of mercury can already be a good reason for cerebral edema to start forming. The skin. Okay, why do we need blood flow to the skin? Well, the skin is the largest organ in the body, and just like any other organ, it would need nutrients. It would need the cells, so the skin would need nutrients. Okay, and therefore it's autoregulated in response to oxygen needs. It helps also, the skin also helps regulate body temperature. So this regulation is neurally controlled and pretty much a very important function of the skin. The skin is a blood reservoir and is also neurally controlled. So pretty much, if we want blood, the first or the prime source of blood, besides of course the venous reservoir, will be the skin. So if we need to increase our blood flow into other organs, for instance, during the skeletal muscle, during our sympathetic response, when you are so scared, and you've heard people tell you, hey, you look pale, you're scared, you look pale. And the reason why you look pale is because there's actually vasoconstriction in your skin, right? And all the muscles, or rather all of the blood, is actually directed into the vital organs that can help you in such instances where you are in your fight flight response. And of course, the skin contains or carries a lot of venous plexuses, okay, below the surface, and it regulates body temperature. So this flow here would be very variable and extremely different. It's from 50 ml, for as low as 50 ml per minute, to as fast as 2,500 ml per minute. Okay, depending on the body temperature, and the flow is controlled by sympathetic nervous system reflexes. Okay. So, as the body temperature rises, for instance, because of exposure to heat, because of fever, because of vigorous exercise, you do not expect yourself really to explode just because you have a lot of temperature, okay, inside you. The hypothalamic signals would reduce vasomotor stimulation of the skin, causing the arterioles to dilate, and so warm blood flushes into the capillary bed, and that would radiate heat from the skin into the surface. And as the temperature decreases, this time it's the opposite. Blood is shunted to deeper, more vital organs. Now, superficial skin vessels will strict strongly, and blood vessels may become trapped. And it causes, and that's the reason why, some people can actually render some rosy cheeks during cold days. And the lungs. Okay, this is an unusual flow, and because the pulmonary circuit, uh, in the pulmonary circuit, the pathway is really short. You could just imagine the systemic circuit pretty much like blood would need to flow from the heart to the different parts of your body, and probably the farthest would be the tip of your toe. However, in the pulmonary circuit, from the heart, it's just, it's just a neighbor. The lungs is just a neighbor. So arteries and arterioles are more likely, uh, or the arteries and arterioles are more like the veins. They're also thin-walled and they have large lumen. The arterial resistance and pressure are much lower than in the systemic. The average blood pressure in the pulmonary circuit is about 24 out of 10 millimeters of mercury pressure, as opposed to the 120 out of 80 millimeters of mercury pressure in the systemic circuit. That's really a big difference, right? And the autoregulatory mechanism for the pulmonary circuit are opposite. When there is actually low oxygen level, it causes vasoconstriction, and high levels would promote vasodilation. And these mechanisms would allow blood flow to oxygen-rich areas of the lungs, because here you want the blood to flow into the areas that are oxygen-rich. Okay. Now the heart, blood flow through the heart is influenced by the pressure in the artery and the force of blood coming in from the ventricle. Now, during ventricular systole, you could imagine what the ventricular systole. Let's close our eyes and imagine the heart during ventricular systole. The coronary blood vessels are compressed because here your ventricles are in a contracted state, and it is compressing every coronary blood vessel that is around it. Okay, myocardial flow would cease because of this, and but no, don't even think that there's not going to be like anything feeding the tissue, because there are stored myoglobin that supplies oxygen to the heart muscle. And then during diastole, when the ventricles are relaxed, there's high aortic pressure, okay, that would force blood through the coronary circulation. So at rest, the coronary blood flow is about 250 ml per minute. Control is probably via myogenic mechanism here. And then during strenuous exercise, coronary blood vessels will dilate. Okay, these are the blood vessels supplying the heart in response to local accumulation of vasodilators. Blood flow may increase about 3 times, from 250 to about 750, or sometimes 4 times. And this is important because the cardiac cells use 65% of the oxygen that is delivered to it. Other cells use only 25. But remember, in your AMP1 cardiac muscle histology, remember that the mitochondria of heart muscles are big. And that's exactly one of the differences between your skeletal muscle and your cardiac muscle. The size of the mitochondria of the heart muscle is 3 times as much, and therefore they can pretty much like uh, make use of as much oxygen in producing ATP. Okay, other cells can use only 25% of delivered oxygen. You cannot afford to have anaerobic um, um, metabolism in the heart. Therefore, oxygen is always being used. That's why 65% of the oxygen that's delivered there is always used. And so, increasing coronary blood flow is the only way to provide oxygen, vital oxygen, to the heart muscles. So, capillary exchange. Now, we're looking at uh, different organs, okay? And we're going to have a generalized view of the capillary exchange and then by looking at several aspects. First, let's take a look at the velocity of blood flow. Velocity of flow changes as blood travels through the systemic circulation. It is usually the fastest right here in the aorta, and they are slowest in the capillaries. Then they would increase slightly again in the veins. Although you would probably say, oh, how would it increase in the veins? Do we have pumping hearts right there in the tissues that could pump the heart from the capillaries into the veins and back to the heart? No. But there are things that can move blood from the veins back to the heart, and we'll discuss it in a few minutes. So speed is inversely related to the cross-sectional area, and capillaries have the largest area, so which means it is more progressively branching. Now, those are the capillaries, and so they will have the slowest flow. Slow capillary flow would allow adequate time for exchange between blood and tissues. Take a look at this, guys. Here's actually your capillaries, okay? And you can see that the capillary has relatively bigger cross-sectional area than the other blood vessels because of the extensive branching, okay? So it has the biggest cross-sectional area, and this is the graph of cross-sectional area. Relative compared to the artery, which is the pink region, and the veins, which is the blue region, the cross-sectional area of the arteries are actually the biggest. And therefore, okay, the velocity of blood flow through the capillary, because there's actually extensive branching right there, and this is actually slow. It slows down in the capillary, which is good because it allows exchange of materials. So vasomotion, we've done this before when we, I think in the first part of chapter 19, when I discussed what vasomotion is. This is the intermittent flow of blood through capillaries. And intermittent simply because this is pushed, the vasomotion is afforded by the closing and opening of the precapillary sphincters. So you may not have pumping heart right there in the capillaries to return blood back to the heart, but the capillaries are not really without motion. These precapillary sphincters provide movement of blood right through the capillaries. So let's take a look at the capillary exchange of respiratory gases and nutrients. Remember that this is actually in the lungs. Many molecules would usually pass by diffusion between blood and interstitial fluid. And by when you say diffusion, and this is passive transport, uh, the law of diffusion simply states that particles move from an area where there is higher concentration towards an area where there's lesser concentration, which means they move down their concentration gradient. Molecules use 4 different routes to cross a capillary. Either they diffuse directly through the endothelial membrane, okay, lipid soluble molecules and respiratory gases do this. They pass through the clefts, all right? They pass through the fenestrations, or they can actually be moved through either endocytosis or exocytosis, meaning pinocytic vesicles, okay, or calveolae. This happens in, among large molecules such as proteins. And if you're going to take a look at this is your capillary. This is a regular um, capillary, and we enlarge this section right here. Take note of this section right here. So there are four ways by which mechanism transport is actually afforded along the capillary. Either they diffuse right through the plasma membrane, okay, from an area of high to low concentration, or they could go through intercellular clefts. This is good among water soluble substances, or they could move through fenestrations. These are the fenestrations, and this is also good for water soluble substances. And then they could be transported through exocytosis or endocytosis. They're being moved by way of active transport via a sac. So, in bulk flow, fluid is forced out of capillary clefts around the arterial end. So here you have the arterial end, and then on one end of the capillary you have the venous end. Okay, so fluid is forced out of the capillaries at the end where you have the arteries, and then most returns back to the blood at the venous end. This is extremely important in determining your relative fluid volumes and blood and in the interstitial space. Bulk flow across capillary walls would cause continuous mixing of fluid between the plasma and the interstitial fluid, and thus maintains the interstitial environment. Okay? The direction or the amount of fluid flow will depend on two forces. One, which you call the hydrostatic pressure, which is the pressure of the water. Another one is called the colloid osmotic pressure. Colloid osmotic pressure is the pressure afforded by certain chemicals or substances inside the blood that acts like a sponge, sucking blood or sucking water and enabling it to stay in the blood, not allowing it to move out. That's actually the osmotic pressure. Hydrostatic pressure, on the other hand, is the water pressure that's actually like pushing along the wall of the capillary. So here you go. Your hydrostatic pressure is a force exerted by fluid against walls, and there are two types of hydrostatic pressure. You have the hydrostatic pressure inside the capillary, and you have the hydrostatic pressure in the interstitial fluid. So in the capillary, okay, blood pressure pretty much tends to force fluid through the capillary wall. So fluid inside the capillary, the water inside the capillary is actually, the tendency of that is to push uh, push it on the wall. So the fluid is actually the tendency of the hydrostatic pressure is to push the water out of the capillary. And usually in the arteries, because the pressure there is greater, the hydrostatic pressure is about 35 millimeters of mercury. And then at the venous end, it's 17 millimeters of mercury. Okay? So your capillary is connected to the arteries on one end and the veins on the other end. On the arterial side, the pressure there is 35. On the venous side, the pressure there is only 17. So these are almost like two different variations. Now, in the interstitial tissue, there's also fluid. Okay, this is actually the interstitial fluid hydrostatic pressure is the pressure pushing the fluid back into the vessel. Here, because we have the lymphatic system. The lymphatic system pretty much like reabsorbs fluid that escapes into the interstitial space. We are assuming that the interstitial fluid hydrostatic pressure is equal to almost zero. Okay. Then you have the second pressure, the second opposing pressure. First one is hydrostatic. The colloid pressure is the sucking pressure created by plasma proteins, non-diffusible plasma proteins, such as your albumin, pulling the water back into the capillary. So they're acting like sponge. And in and the oncotic pressure in the inside the capillary is roughly about 26 millimeters. Now in the interstitial space, okay, the fluid osmotic pressure is inconsequential because the interstitial fluid has very low protein content. And therefore, the interstitial fluid pressure, or oncotic pressure, is roughly assumed to be only 1 millimeter of mercury. So if we're going to put together in a formula the relationship of the hydrostatic and osmotic pressure and how they interact with one another, the net filtration pressure, just to take a look at the net filtration pressure, pretty much it comprises all forces acting on the capillary bed, where you have the hydrostatic pressure in the capillary and the oncotic pressure in the interstitial fluid. These are all both pressures that are pushing what do you call this? Pushing a fluid outside of the capillary. And then this other group here is the hydrostatic pressure in the interstitial fluid, and the oncotic pressure the inside the cells or the capillary is actually the one that that sucks the fluid back in the capillary. So this one moves fluid out, this one moves fluid in. So the net pressure of all the forces that are pushing the fluid out minus the net pressure that is going to retain the fluid in is actually your net filtration pressure. Okay? Usually the net fluid flow at the arterial end is going out because of the large hydrostatic pressure in the artery, and therefore we are doing filtration in the arterial end of the capillary. The net fluid flow at the venous end, though, the direction is different. It is actually reabsorption. So here on the arterial part, the fluid really goes out. In the venous end, it is reabsorbed. So more fluid leaves at the arterial end than is returned at the venous end. So that means if there's nothing that's going to be controlling the fluid that goes into the interstitial space, we are going to be bloating, and we are all going to have like edema in the right there in the tissue level. However, excess interstitial fluid really is reabsorbed back into the blood right there in the left subclavian vein via our lymphatic system. So our lymphatic system is the one that helps circulate the fluid. All right. So here is actually something to look at. Right here is 35 millimeters of mercury pressure. Over here and this other side is 17 millimeters of mercury pressure. So you could just imagine, take a look at the arrows, that on the arterial bed or on the capillary bed close to the arteries, you know that fluid is actually moving out. And then on the bed where it's close to the veins, then fluid is actually being reabsorbed. Here it's reabsorption. Over there is actually filtration. And okay, so here's on looking it up close, or if you're going to be looking here up close, let's take a look at how we're going to look at this. See what we know about the pressure in the past two slides. to determine the net filtration pressure, okay, at any point. So the net filtration pressure is the pressure driving the fluid out of the capillary. And so to do this, we calculate the outward pressure, which happens to be the outward pressure happens to be your um, here you go, your hydrostatic pressure in the capillary, which pushes the fluid out. Equivalent is it's equivalent to 35 millimeters of mercury, and then the osmotic pressure, which is in the interstitial fluid, which pulls the fluid out of the capillary. So here, the pressure is coming from the capillary and pulls out, okay, and it's only equal to 1 millimeter mercury pressure. So you add both of them because that's actually supposed they're doing the same thing. So you add both of them, 35 plus 1 millimeters of mercury pressure. Then you subtract the total of the uh, osmotic pressure in the capillary that is doing the reverse, which is, that's why you're going to subtract it because it's doing the opposite. The osmotic pressure in the capillary pulls fluid back into the capillary and is equivalent to 26 millimeters of mercury pressure. And also the hydrostatic pressure in the interstitial space, which is really negligible, so it's really zero. Okay, we put it as zero because there's really not that much pressure in the interstitial fluid because your lymphatic system is reabsorbing the fluid that gets into the tissues anyway. So that's actually going to be this section right here, all right, which is 0 plus 26. So you add them both, 35 plus 1 is 36, 36 minus 26. Do your math. 36 minus 26 is equal to 10 millimeters of mercury pressure. That is your net filtration pressure. Normal on a standard, okay, most humans will have a net filtration pressure of about 10 millimeters of mercury pressure. As a result, fluid moves from the capillary into the interstitial space. You could just imagine how low this is. So are you telling me if you lose blood, what is the consequence of this if you lose blood? If you lose blood and this 10 millimeters of mercury pressure drops to zero, drops down really to zero. If you lost a lot of blood, then the pressure of the arterial pressure drops down to about 25. You're not anymore going to have tissue perfusion. And so you could actually get into hemorrhagic shock. Uh, that's why hemorrhagic shock happens because when this is reached, when this is not met and you have only zero because up here you have 25, so your blood is not anymore going to feed your tissues. Blood pressure is not anymore going to feed the tissues. So this is now the opposite on the venous aspect, and we mentioned that in the venous aspect what happens is reabsorption, which means the flow of blood is opposite. So right here we are looking at calculating the net filtration pressure, okay, where the sum of the hydrostatic pressure in the capillary pushes the fluid out of the capillary. The pressure pretty much has dropped because of resistance along the capillaries. And together with this, you add the osmotic pressure in the interstitial fluid, which pulls the fluid out of the capillary. Okay, and together, okay, they will form 17 plus 1 in our example, all right, and then the next group will be the one that pushes the fluid in, and here you have 26 millimeter of mercury pressure, which is the osmotic pressure in the capillary, and it pulls the fluid to go into the capillary, plus, okay, the hydrostatic pressure in the interstitial space, which is 0 because of your lymphatic system. So pretty much 0 plus 26. You will come up with negative 8. So because it is negative, okay, the net filtration pressure at the venous end is negative, and this means that what's going on here is not pushing fluid out, but it's actually taking fluid in. So this is reabsorbing fluid. So at the venous end, fluid from the tissue has to move into the capillary, okay, from the interstitial space into the capillary. Okay, so pretty much we're done with the physiology of controlling that controls pressure in the bloodstream. We're now going to discuss some homeostatic imbalance. Remember, this is AMP1. This is not clinical, so we're just going to look at the very simple ones, like edema is an abnormal increase in the amount of interstitial fluid and can be caused either by an increase in outward pressure, which means the driving force out of the capillary, or a decrease in inward pressure. And an increase in capillary hydrostatic pressure would accelerate fluid loss from the blood. This could result very much, edema could result pretty much from incompetent venous valves, localized blood vessel blockade, congestive heart failure, or high blood volume. Okay, and it could also be caused by an increase in the interstitial fluid oncotic pressure, okay, from an inflammatory response. Remember that inflammation would increase capillary permeability and allows protein to leak back into your interstitial fluid. And that's actually one of the actions of histamine. And pretty much it causes large amount of fluid to be pulled into the interstitial space. So a decrease, it can also be caused by a decrease in capillary colloid osmotic pressure that hinders fluid return to the blood. Okay, and could be caused by a condition which you call hypoproteinemia. Okay, low levels of plasma protein is actually caused by malnutrition or diseased liver or glomerulonephritis. Okay, edema can also be caused by decreased drainage of interstitial fluid through the lymphatic vessels and have been blocked by diseases or possibly surgically removed. Excess interstitial fluid in subcutaneous tissues generally causes what you call pitting edema. And edema can impair tissue function as a result of increased distance for diffusion of gases, nutrients, and waste as well between bloods and cells. Now, slow fluid loss can be compensated for by, some renal mechanism, but if it is fast, the rapid onset may have serious effects on circulation. And I think it's a picture. All right, here is a picture of pitting edema. All right. So we're now going to get into the circulatory pathway. And pretty much the pathway really is just a flow of blood from the heart to the lungs and then back to the heart, and pretty much is um, an avenue for the lab. Okay, these are all laboratory. For instance, pulmonary circulation is a very short loop that runs from the heart back to the lungs, and then back again to the heart. Meanwhile, your systemic circulation is a very long loop, which is going to be directing blood from the heart to the arteries, and then into the tissues, and then back into the veins, and then back into the heart. Okay. And this is a schematic flow chart of the pulmonary circulation, which I'm going to leave to you guys. It's really very easy. I just thought that I would like to put this here uh, just to remind you. If you will have any questions on any of these circulations, guys, I would advise you to either to contact me, and I would, and of course, reach out to me during our QA session, either on a Tuesday or on a Thursday. Okay. All right, let's take a look at, just very briefly before we end this, the important differences between systemic arteries and veins. Make sure that you know arteries run deep. This is part of the lab, but I am just what do you call this? Extending my lecture, okay, so you will understand it better. The arteries run deep, and the veins are very peripheral, superficial. Okay, they run deep on arteries run deep only, but veins run superficial, deep as well as superficial. Deep veins would share the same name with a corresponding artery, just so you will know in your exam. Superficial veins do not correspond to any arteries. Okay, the venous pathway are more interconnected. Unlike your arterial pathway, venous pathways have more interconnections. The veins have more than one name, making venous pathway really harder to follow. The brain and the digestive system have unique venous drainage system, and they are called dural venous sinuses. And I think the dural venous sinuses are part of the things that you need to know in the lab. Want you to know that you do not need to extend yourself too much in the blood vessels. We gave you a list at the beginning of the lab, the list of the names of blood vessels that you are being held responsible for knowing. Just stick with those, all right? Do not overextend yourself. And this is actually a schematic flow of blood outside of the pulmonary, which is the systemic. The blood is actually is pumped by the heart through the aorta, okay, and it goes into the uh, systemic circulation, and right there you go, the systemic circulation in the head, and then from there capillaries pick it up and is perfused into the tissues, then back into the veins, and then back into the right side of the heart. Okay, goes right through again into the pulmonary trunk, because here the blood is oxygen poor, so it needs to go run through the pulmonary circuit so that in the two lungs it could pick up oxygen and then go back to the left side of the heart, and is now going to be pumped out again via the aorta. All right. So just know in the lab that oxygen rich blood are usually red. The arterial blood is usually red, and oxygen poor blood is usually shown in blue. And this is only in diagrams that you will see in the textbook as well as in the model. Okay, so the diagrams that you see in your textbook show pipe diagrams. Okay, and so the tips for memorizing them pretty much will be usually the name of the blood vessel reflects the body region that it is passing through. Okay, such as your axillary, your brachial, your femoral, or the organ that it is serving, or maybe the bone that it is passing through. All right. So very much make sure that you know the arteries and veins run side by side. They tend to run side by side in many places. They also run with nerves. Systemic vessels do not always match on the right and left side of the body. It's not always true that it is bilateral. Okay. Almost all vessels in the heads and the limbs are bilateral and symmetrical, but some very big or large vessels or trunks are very asymmetrical.